My name is Zach, and I'm going to talk to you today about anomalies in the Radio Neutrino Observatory in Greenland and how I've found them. So rno-g, we've heard a lot about ultra-high energy neutrinos already today. rno-g is one of the neutrino telescopes that we're currently building, trying to find them. Here in Summit Station, Greenland, right in the middle of the Greenlandic ice sheet, we're building 35 of these independent stations. We drill 3 100-meter holes in the ground, and we stuff them full of vertically polarized and horizontally polarized antennas. And then on the surface, we have 9 sort of Christmas tree-looking log periodic dipole antennas, and some of those are pointing up in order to view cosmic ray air showers, and most of them are pointed down into the ice to look for neutrinos. We currently have 7 stations that are currently built and taking data. And, you know, we've seen this picture a bunch today, so I'm not going to go through it too much, but we like neutrinos because they point directly back to their sources. And if we zoom in a little bit, you can see that when a neutrino does come in and interact with something in the ice is a dielectric medium. So you get this charge anisotropy, and you get this Ascarian radiation mechanism along the cone, and you can get a coherent pulse of radio emission that either travels directly up the cone into our instrument, or because of the changing index of refraction in ice, you can also get a travel path that goes up and then curves back down into the detector. So what kind of sources are we looking for? In terms of point sources, GRBs, their afterglows, young magnetars, which, as we heard yesterday, could be concurrent with FRBs, and also maybe some blazars, specifically FSRQs. And so wouldn't it be great if, like, one of the brightest GRBs of all time just went off and happened to be like really, really close? And that happened in the end of last year in October. And it's actually pretty amazing because this is a plot of our instantaneous sensitivity. And so the GRB happened at a declination of 19 degrees, which is like right in the perfect part of the sky where we're always sensitive. But then we actually, like, earlier in that day, we just powered off all of our stations for the winter because it was getting too dark. So, you know, what are you going to do? That's a shame. But we need to be ready in the future to be able to quickly, rapidly respond to events like this so we can participate in the multi-messenger astronomy community. So if this wasn't a PDF, you'd see my neutrino zooming through our signal chain. But basically, neutrino gets emitted from the source, interacts in the ice. Ideally, the radio pulse is seen by our antennas, moves through our amplifiers and all of our cables into our data acquisition system. And then Summit Station is in the middle of nowhere, so we built our own LTE network in order to get the data from all of our stations to the big house at Summit Station. From there, it goes by satellite to DESY, where all of us graduate students try to figure out what to do with it. And for the first season, we were transferring about 10% of the data at any given time. But in the future, when we build, you know, the whole array, that's going to drop to about 1 to 5% of the data. So we need to filter, and we need to filter here, and we need to filter here at the big house. So there is a compute center. There's not like a ton. We just basically have a big server rack. So we need to be smart about how we choose which events to send further south. And so what do our data look like? Well, each antenna, you get a sort of time series trace here of 2048 samples taken at 3.2 gigahertz. So this corresponds to about 640 nanoseconds. And you can do a Fourier transform to get the frequency content. But then, you know, if you're only looking at this, then you just have the timing information. If you're only looking at this, then you just have the frequency information, but you don't have the time. So what you can do is you can combine these two in sort of like a binned method. It's called a short time Fourier transform, an STFT, and you can get a sense of how the frequency content evolves over the time of the trace. And you can use these sort of common machine learning tools, this sort of auto encoder decoder system, where you take these images and you train a network to encode the information down into a compressed latent space. And you train at the same time a decoder that comes out of that latent space to make a reconstruction of the image, right? And so I've done this with the 4 triggering antennas at the bottom of the detector, our phased array. And basically, you can compare the original to the reconstruction pixel by pixel, and you can compare them like how well the network reconstructs. It's going to have an easier time reconstructing the noise environment, these sort of thermal fluctuations, than it will signal events. So what does this look like? This is again just sort of these sort of thermal noise fluctuations, and this is you see here this MAE score is right here in the sort of peak of our heavy-tailed log normal distribution. Another common sort of noise that we see is CW, continuous wave. So this is basically people running around with walkie-talkies. This one in particular is at 403 megahertz, which is a weather balloon that is sounding. So we can actually use things like this for calibration, because if it's a weather balloon that's also being launched from Summit Station, they have GPS information. We can use that to sort of track the signal around the array. So that's actually can be pretty useful. We also, very highly anomalous, we have these onboard calibration pulsars on our stations. And so you can see here the clear times that my colleague Christoph was pulsing at the end of the season, right? And then we start getting into some of the weird things that I'm finding. So this happened during a high wind period. And at first you think, oh, wow, this is sort of great. This is the Goldilocks kind of event that we've been looking for. You see the direct ray that I was showing you earlier, and then you see a little bit later, you see the refracted ray coming in from the top. But there are a few dead giveaways that we know that this is definitely not a neutrino. And that's first, you see down here, there's maybe the start of a third pulse. And also you see this big dip in the frequency spectrum. If this was a neutrino, you'd expect a more of a linear relationship, maybe with stronger lower frequency content kind of going down to the higher frequencies, but definitely not this clear big blip. Then you see this sort of very high sort of peak of anomalies. And if you look at the different stations, we see it very strongly in station 2.1 and station 2.3. But as you look in some of the others, maybe you definitely see something here, but it's a little weird, and maybe not so much in these stations. So what could this be? Well, it turns out that there's another experiment at Summit Station called ICESat-2. It's a NASA experiment where there's a satellite going overhead, shoots a laser down, and then that reflects back up, and they can measure things like trees and snow depth. And Summit Station, once a month, they go out on a snowmobile and they take actual measurements to support this experiment. And Summit Station doesn't really keep a log of how often people go out on snowmobiles and do stuff, but this is tracked every month. And then you can see the difference in time, about 15 minutes between the stations, and that's about how long it takes for the snowmobile to go back and forth. So now we know what snowmobile events look like, and we can use that to help discriminate in the future. We also get to see some weird glitches in the detector. So first you see these block offsets. You see this channel down here is kind of going all over the place. This comes up as anomalous, and this is just due to the way that our FPGA digitizes the signal. And this probably happens due to unstable bias in the supplied voltage. And the good news is that this is fixable in level 1 calibration. So problem solved. This one is also pretty cool. This is, I'm sort of calling it a mega block offset event. This is one of the most anomalous sort of events that I found so far. And what's interesting here is that after this event happens, we think this is because of a drop in power, although in our housekeeping data, you don't really see anything obvious. But after this occurs, this big spike you see a separation here in the blue and orange line. And what that means is now, instead of kind of having an offset, we're actually getting some sample switching, where the signal is scrambled. And this is really hard to see unless there's some sort of impulsive event. So you see in channel 1, these look like pulses, but in channels 0, 2, and 3, this is clearly scrambled. And if you look at these plots down here, again, the blue and the orange line are on top of each other. Here, they're separated. And so this is important to figure out when this is happening, because in the lab, it looks like this does always happen in the same way every time. So again, we can fix this, we can solve it, we just have to know about it. If you fix it, you unscramble the data, you lose some samples on either side of the trace, but we can deal with that. So another problem solved. And now we're actually going to get into a little bit of astrophysics. So back in September, I found this cool, I was calling it an anomalous low threshold event. Didn't quite know what it was at the time, but then as we were starting to study the sun, we looked at some e-Callisto data, and it turns out that this is actually a solar flare. And you can see here, kind of concurrent with this e-Callisto data, where you see this big spike and this other follow-up, you see in our sort of anomaly detection, very similar shape at the exact same time. And so after this, I went ahead and I trained a new version of the network on a so-called solar model. And that's with a Butterworth filter up to 250 megahertz. That's a pretty good limit for where these sort of bursts are most intense. And running over the data, again, you can see there's a really clear little blip here. Turns out that was another solar flare. So now you can use this as sort of a real-time monitor to look for more solar bursts, which again, really good calibration opportunity across the entire array. So what about neutrinos? Because that's what we're here for. So we have some new simulations now where we use the actual measured ADC counts in the detector to make a real representation of what the neutrinos would actually look like in our detector, because it's really easy to simulate neutrinos, but it's really difficult to simulate all the different components of our signal chain. And you see in this plot on the right, good news is the neutrinos come out as being highly anomalous. And so in terms of figuring out what kind of information we actually want to send south, you take this big sample, like a month of data from one station. I remove the CW information because we know CW pretty well. And then if you just prioritize the high MAE, you can cut away a big chunk of noise while retaining a pretty good fraction of the neutrinos. And you can increase the purity from 0.043 to 0.077, which doesn't sound like much, but that's about an 80% improvement in neutrino purity. And it also effectively doubles our satellite transfer rate. You could make a more aggressive cut out here on the tail, which might be useful in the future. But we don't expect to receive too many neutrinos, on the order of like 1 a year when we're at full operation and we're still learning a lot about the detector. So for now, we probably want to be pretty conservative and still send a lot of data south. And so I'll show you a couple of more interesting events that I found more recently. I want to start off by saying this is definitely not a neutrino. Again, because of order of 1 per year. But it, and we see kind of a few interesting events here. So again, we don't expect to see many together. But this does kind of look like one if you look at the simulations. And I'll answer your question. Yes, there is an ATEL that happened on the same day for a flaring blazar, but it was in the southern hemisphere, so no connection there. But in terms of actually just working on other real events that we're more confident about, if you go to ICRC next week, you can see a presentation on our cosmic ray air shower candidates. And if you run this same network architecture, but on the surface component of the detector, our cosmic ray candidates, Aldrin and Armstrong. Aldrin lays about here in the distribution, and Aldrin is like way off the board, somewhere over there. And they also come up as being highly anomalous. So that's a really nice validation. So to sum up, neutrinos simulated and cosmic ray candidates are highly anomalous. New noise classes and glitches have been discovered and mitigated. The active sun can be used as a calibration source, and there's sort of these characteristic burst shapes that we can use to help distinguish. And the thing to know, this is just one component of our overall filtering and multi-messenger response strategy. So it's nice to know that we can do something with this one single score, but there's going to be a lot more that goes into our actual responses. And there's a lot of room for improvement. So these models are super simple. There are more complex 3D methods, more impulsivity parameters that we can use to hopefully get down to some better efficiency and purity. So, yeah. Yeah.
For the solar flares, you have a metric on how efficient you are in detecting them after you found out. So
So there are actually, so I think these sort of type 2, type 3 bursts, we're approaching a solar maximum. So these are becoming more and more frequent. Callisto just has these like one a day, maybe. We don't always see them. But so what's nice is that then instead of always chasing the Callisto data, we can just use this to see when we do see them. And then I have another colleague who's actually doing the direction reconstruction of these. So basically I monitor, if I find one, I send it to her and gives her more data. So
yeah, you also have simulation for those?
we do not have any simulation for this, so yeah.
What are the cognitive capabilities of this sharing effect technique?
So we just had a paper come out. Another one of my colleagues worked on the direction reconstruction, and it's looking like I think about 5 degrees, 2.5 if you look in 1D. So
okay, because you can combine both signals, like the one directly with the code and the one.
Yeah. And so that really depends on like whether or not you're like your on cone or off cone sort of viewing angle. Yeah.
Right.
Very nice question. Why is there a season?
Why is there a season?
Yeah, why do you have to turn off?
So right now, the array is powered mostly by solar. So we have these solar panels that collect data, and then in Greenland it gets dark for most of the year, in the winter. But actually we're also installing wind turbines in some of the stations. They're not working perfectly yet. But hopefully they will come online in the next couple of years, and then we can continue to get a lot more live time in these periods, which would be nice because it's also a quieter period. It should be less noisy. Yeah.
What's so special about orbit and upstorm? I mean, you must see cosmic rays all the time, right? But are these more very energetic events, or?
Yeah. So from a design perspective, we do expect to see like one cosmic ray per station per day, but we're not quite there yet because of the way the trigger has been developed so far. But in a couple of years, I think we'll kind of hit those benchmarks.
Can you estimate about the energy of these events?
I'm not entirely sure. I think we're still in the process of making sure that they are cosmic rays.
Yeah.
Yeah.
Okay, let's thank Zach again.